Welcome to video 4.9 in our first Principles of Astrophotography series. In this video we discuss the energy source of supernova remnants, which is collisions between rapidly expanding supernova remnants and the interstellar gas.
In the last video we discussed the energy source for diffuse and planetary nebulae, which is ultraviolet photons from one or more hot nearby stars. This video is based on section 4.9 of our First Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensibility. Principle 70. Emission nebula ionization. Diffuse and planetary nebulae are photoionized by one or more nearby hot stars. So that's photoionization. While supernova remnants are ionized by collisions of expanding supernova remnants with interstellar gas.
So this is a review. We talked about this in the last video, and we talked in detail about the photoionization of diffuse nebulae such as the Orion Nebula and planetary nebulae such as the Ring Nebula. And now we want to focus on the ionization of supernova remnants. And this is caused by collisions between the expanding supernova remnants and the interstellar gas. So the interstellar gas is just hanging out there. A supernova explosion is when a star explodes and gets completely ripped to shreds by the explosion. And those remnants of the explosion are expanding at extremely high rates into the interstellar gas. They're ramming into that interstellar gas, and they're not photoionizing, but ionizing, collisionally ionizing those atoms in the gas. So for example, and this was quite a revelation to me when I looked at these data, supplied by Richard Walker, author of the Spectral Atlas for Amateur Astronomers. And he supplied this data to me, and I went, wow. And in his book, I noticed this too. There's two peaks for the forbidden doubly ionized oxygen line, where there should have been one. This one should have been 500.7 nanometers, but there's one that's a little higher than it, and that's called Redshift, redshifted line. And then there's one a little bit lower than it, which is a blueshifted. And why they call it redshifting and blueshifting, redshifting just means that the wavelength gets increased beyond what it should have been. If you just remember that red is up here, the limit of the visible spectrum is 700 for red and about 400 for violet. So a redshifted line is one whose wavelength is shifted toward the red and it's increased, and a blueshifted line is, and you see the same thing here for the hydrogen alpha lines. It's got a redshifted and a blueshifted. You see also for the sulfur lines, you see it for the hydrogen beta lines. So where does this come from, this shifting of the lines? And I might point out that in a later video we're going to talk about the implications of these Doppler shifts of these lines on the selections of filters. These this spectrum right here, the sort of teal greenish colored line, is a spectrum of a chroma 5 nanometer filter, 5 nanometer bandwidth filter. And our filters are 2.5 nanometers in bandwidth. So our filters would look something like this, and we pretty much miss both lines on the Crab Nebula. So
this is why it's so important to understand, so you can get the right filters.
So you know what if you understand the scientific foundations, that's what this whole book is about, then you can make informed choices about your equipment. And we have these 2.5 nanometer filters, but I think we'll probably want to get some that are 8 or 10 nanometers, which is nice because they're cheaper than the 2.5 ones. So and we'll talk about this in a later video, but the important thing to notice here is that for supernova remnants that are expanding at such high rate, you may be throwing out the baby with the bathwater if you're using super narrowband filters. Okay, so let's explain though what's going on here. And by the way, these two little marks here, you might or might not be able to see them. They're a vertical yellow line and a horizontal yellow line. They're pointing out the Crab pulsar. And this was a photograph taken by the C-Star S50, and we observed the Crab pulsar. So we're pretty darn proud of that. And Ren spent 2 or 3 days trying to process the data, drizzle the data, right? I mean, we spent a lot of time trying to do that with this.
I was pretty new to it at the time, but it's still, I think we'd already done a few objects, and this one was so hard. Yeah.
Yeah, but this one mattered a lot to us. So that was taken with the C-Star S50, which just says a lot about that telescope. Plus, it says a lot about Ren's
The trick was trying to not stretch it too hard that you blew out the pulsar, and still getting a pretty enough object that it still looked nice with the pulsar in it.
Yeah.
Rough.
Yeah. Tough job.
All right, Principle 74, Doppler shift. Rapid expansion of transparent supernova remnants split each emission line into a longer wavelength, redshifted line, and a shorter wavelength, blueshifted line.
So the Doppler effect is something that you've all experienced because you've heard cars approaching or trains approaching, and the sound that you hear is and then when it passes you, it goes and it doesn't go it goes, it's a high pitch, and then while it's passing you, it quickly goes down to a lower pitch, so that when it's approaching, that's a blue shift. So if this star is approaching the observer, then its wavelengths get scrunched because between the emission of each wavelength, it's moved toward you, and so the wavelengths are getting scrunched. So the wavelength, it's a shorter, aka blue shifted. Doesn't mean it's going to be blue. It just means that it's shorter wavelength toward the blue. And that's on approach. And then if a star or any object is moving away from you, then between the emission of each wavelength and the next, it's moved away from you, which has stretched that wavelength out. And so this is a longer redshifted wavelength when it's receding. So quiz question. The universe is expanding, and therefore when we look at distant galaxies, are they typically blue shifted or redshifted?
If they're going away from you, they should be redshifted.
That's right. In fact, that's how we measure distances to distant objects. We look at their spectra, we see how much that wavelength has increased or redshifted. We compare it with the Hubble expansion constant, and we get an estimate of how far away that object is. Pretty cool, huh?
Pretty cool.
Yeah, so this is, and then I also want to talk about the whole transparent idea. This is our photograph of the Crab Nebula, and it doesn't really look very transparent, to be honest. But if you look at each frame, and I don't know if, I can't remember for sure, it was a year ago or more that we took this image, but each frame is pretty faint, right? You're just seeing a little bit of wispiness, and then you're stretching it, and you're drizzling it, and trying to get it out. But the important fact here is that we wouldn't see these two Doppler shifted lines if the supernova remnant weren't transparent, if it were opaque. So by transparent, I mean that you can see photons that are emitted both from the front side of the nebula that's close to you, the supernova remnant that's close to you, and from the back side that's farther away from you. So the front side of this expanding supernova remnant is moving toward me and should therefore be blue shifted. And then the back side of that supernova remnant is moving away from me and should be redshifted. If it weren't for the fact that and this is something Richard Walker points out in his book, that if it weren't for the fact that these supernova remnants were transparent, then you would only see one line here. You wouldn't see the redshifted line.
Right.
Because it'd be obscured by this stuff.
By the stuff coming towards you. Yeah.
Exactly. So that's where this whole transparent supernova thing comes into play. I just think it's really cool.
So the supernova remnant is not moving towards us as a whole. It's just expanding, so the front is moving toward us and the back is moving away.
Well, and that's actually a great question. I do not know whether the Crab Nebula happens to be moving away from us or moving toward us. It's probably doing one or the other.
Well, the blue and the redshift is caused by the expansion of the remnant, though.
And the important thing is that the motion of that, the overall motion of M1, the Crab Nebula, is really slow compared to with this rapid expansion of the nebula. So it almost really doesn't matter whether it's, well, it does matter, but it doesn't play much of a role. So just to give an idea about how fast this thing is moving, we did a little calculation. The fastest fighter jet, and we talk more about this in the book, the fastest fighter jet goes about 2 kilometers per second. So that's 2,000 meters per second. And a mile is about 1,600 meters, isn't it? You know that from your running days, 1,609 meters, pretty sure. So that's about a mile per second, or a little bit more than a mile per second.
Wow.
For the fastest fighter jet flying high above the Earth's atmosphere. It would take 2.2 days for it to get from Earth.
Well, if it could fly high above the Earth.
If it could, yeah. But at the speeds that it can fly near Earth, it would take 2.2 days for it to get from the Earth to the Moon. Sorry. The Earth-Moon distance is 385,000 kilometers. This, you can't see it very well, but the diameter here of the Earth and the diameter of the Moon are correct to scale, and they're scaled right for the distance between them. So, and this is a Wikimedia image, which we've just been so grateful for the images that are available on Wikimedia, and I mentioned in the acknowledgments that, yeah, Wikimedia is a tremendous resource, and here's the attribution for that. So Wikimedia Commons, if you really want to know, this is kind of a side, sorry about that, but it has hundreds of millions of images that are available either for free or just with the expectation that you do proper attribution, but it's called a Creative Commons. It's a tremendous resource. It's been hugely helpful. All right, so end of story there. But the crab remnants travel at 930 kilometers per second. And I actually worked that out based on the Doppler shift. It's an easy calculation. We do it in the book. Based on how much those lines are shifted, which is I think 3 nanometers or something like that, you can work out using the Doppler equation how fast the remnants are expanding, and it's about 930 kilometers per second. So compared to 2 kilometers per second, 930 is about 1,000, so it's 500 times faster than the fastest jet.
It's a bit.
And if you work it out how long it'll take to get from the Earth to the Moon, those remnants take about 7 minutes. So I think what's important to point out is that these supernova explosions are tremendously violent events. I think they're the most violent events that occur in our universe at all. And maybe some of these gamma ray black hole interacting are more violent, but these are incredibly violent events. They rip an entire star into shreds, and they send those shreds out into space at extremely high velocities. The Crab Nebula, the supernova explosion that created the Crab Nebula, was observed by Chinese astronomers in the year 1054. And then later, and they described where they saw it in the sky. They saw a big, it lasts a few, probably a dozen or more days, as a bright new star in the sky, and then it fades slowly. But then since then, since the year 1054, astronomers have seen that nebula expanding, and that's what we have for the Crab supernova remnant.
Crazy.
So the point here is that this violent expansion of the remnants of this supernova, which left behind this little pulsar, little neutron star, those remnants are expanding out, ramming into the interstellar gas and ionizing the gas, and that's why we can see the Crab Nebula.
And the pulsar is just this cute little guy that's spinning super fast.
Spinning at a super high rate. That would be like going on the amusement park ride that makes you sick times 10. That's just a tiny core, just maybe 10 kilometers worth of taking just the central core of the star that's left over from the supernova explosion. Thank you so much for watching.
And we'll see you next time.